So for number 1 here, the first step that we have to do with any of these equations is to be able to look at it and recognize from the form of the equation what conic section it's going to make. So for number 1 here, we have both x and y are both squared, so that means it can't be a parabola. The fraction here where there's a different number underneath them means that it cannot be a circle. If those numbers were the same, it would be a circle, or potentially a circle. So that means it's either a hyperbola or an ellipse, and the fact that it's a minus between them tells us that this has to be a hyperbola. So now that we know the shape, we can pick out the pieces. In a hyperbola, whichever variable comes first and is positive is the direction that it opens. So since the y is the positive one, that means that this is going to open vertically like that. So let's find the center of this. The center is still going to go off of the x and y. So x plus 1, remember it's always x minus the x coordinate of the center. So x plus 1, we have to think of that as x minus a negative 1. So that puts us at negative 1. Y plus 3, again, think of that as y minus a negative 3. So that puts us at negative 3 for the y coordinate. So there's our center at negative 1, negative 3. Next, we have our transverse axis. Remember, the transverse axis goes in the direction of opening. So we have the 9 there under the y. That's a squared. Or actually, I should be careful. It's with the y. That should be our b squared. But that means that b is 3, the square root of 9. So in that vertical direction, we go from our center, we go up 3, and we go down 3. And so our box that we're going to use to graph this, that's the top and the bottom limit of it. Then for the x, that's over 16. That's a squared, so that means a is 4. So from that center point, we go 4 units to the right and 4 units to the left. That completes the box that we use to graph this hyperbola. Now at this point, we know where the vertices are. One vertex, since this opens vertically, is on the top of the box there. That's going to be at a negative 1, 0. The other vertex is at the bottom of the box here. That's at negative 1, negative 6. We know that we have asymptotes. One goes there. One goes there. They go corner to corner through the box. So from each vertex, the hyperbola goes out and approaches the asymptotes. So on top like that, and on bottom like this. So we have graphed the hyperbola, and that's all I'd ask you to do. So if you did that much, I would be very happy. But let's look at a couple other things. Let's locate the foci. To find the foci, we have to know c. And for a hyperbola, a squared plus b squared equals c squared. So we have a squared is 16 here. B squared is 9. That adds up to 25. So c squared equals 25, telling us that c equals 5. So what that means is along that transverse axis, we go 5 units from the center. So 1, 2, 3, 4, 5. That gives us one focus there at negative 1, 2. Or down 5, 1, 2, 3, 4, 5, giving us a focus there at negative 1, negative 8. So those are the foci. The other thing I could find are the equations of those asymptotes. I know that the slope of this asymptote here is 3 over 4, b over a. This asymptote here is going to be just the opposite, negative 3 over 4. we know that both of them go through that center point of -1, -3. So for this asymptote here, that coordinate would be y plus 3, because that's y minus a -3, equals that slope of 3/4 times x plus 1, x minus the -1. And then, of course, the other one is the exact same equation. We just changed the slope to -3/4. So those are the equations of our asymptotes. Let's look at the parabola. Well, first, I guess I should talk about how do we know that's a parabola. Well, a parabola is the only conic section in which only one of the variables is squared. So here only x is squared, and y is not. So that tells us that this has to be a parabola. Now, because it's the x that's squared, that tells us this is vertical. Either opens up like that or down like that. We know the vertex is going to be at 3, 2. X minus 3 gives us 3 as the x coordinate. Y minus 2 gives us 2 as the y coordinate. So if I set up our axes here, 1, 2, 3, 1, 2, there's that vertex at 3, 2. Now, next we have this item right here, which multiplies the variable that is not squared. That's a -8. Remember, that number is equal to what we call 4a. Or 4, I should be careful. Depending on what notation you're looking at, 4a, this textbook uses 4p, where p is used for that distance from the vertex to the directrix and then the vertex to the focus. So we solve that for p. We're going to divide by 4. -8 divided by 4 is -2 equals p. So p is -2. Now the fact that p is negative tells us that this parabola opens downward. It is saying that the focus is 2 units below the vertex. So from the vertex we go down to, that's the focus. That's going to be at 3, 0. The directrix then is 2 units on the other side. So the directrix is up here at y equals 4. Now to plot our parabola, we already have the vertex here. Let's find another point. Well, remember, a parabola is defined to be all points that are the same distance from the line, that directrix, and from the focus. So if I go straight off to the side of the focus, I know that's 1, 2, 3, 4 units from the directrix. So if I go straight 4 units to one side, that's 4 units from the focus and 4 units from the directrix. I go 1, 2, 3, 4 units to this side. That's 4 units to the focus and 4 units to the directrix. So I know those 2 points are on the parabola. So then we can just go from there. So this is kind of a wide parabola here. Now, since we've put out 2 of them, let's put out the other 2 and how we know what shape they are on the graph. So if I were to give you the equation, a third equation here, x plus 2 squared over 25 plus y minus 1 squared over 9 equals 1. And another one here, equation 4, x minus 1 squared plus y minus 3 squared equals 16. Number 4 is kind of obvious. It's the only one where the x and the y aren't divided by anything. And it's the only one where we have both x and y squared, and the opposite side here is not a 1. We know that number 4 there is a circle. Now, we haven't talked about circles with the conic sections, but we talked about those a few weeks ago in graphing. 3 over here, we have both x squared and y squared, so that eliminates the parabola. Can't be a parabola. The fact that it's divided by different numbers here tells us it can't be a circle, so we know this is either an ellipse or a hyperbola. Well, since it is plus here, that tells us that it has to be an ellipse. So if we go to graph that, we have x plus 2, so that tells us x is at negative 2. Y minus 1 tells us that y is at positive 1. There's our center. So center is at negative 2, 1. Now here, it doesn't matter which one comes first or second. What matters is which one has the larger number underneath it. X has 25 under it. That's saying a squared is 25, so that a has to be 5. So that's under the x. That means we go in the x direction. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That makes the sides of the box that would contain this ellipse. Under the y, we have 9. So b squared equals 9, telling us that b equals 3. So from that center, we go up 3 and down 3, forming the top and bottom of that box. So the box that contains our ellipse looks something like that. So now we can draw in our ellipse. It's going to be tangent to all 4 sides of that box. So there's our ellipse, sort of. Again, that's all you would need to do to graph that, but let's talk about finding the focus, the foci. For an ellipse, it's a squared minus b squared equals c squared. A is always the larger one, so that's the 5, so that's 20. A squared is 25. B squared is 9, so it's 25 minus 9 equals c squared. So 16 equals c squared. You square root that to get that c equals 4. Now remember, c is the distance from the center to the focus. Since the longer axis is horizontal, we go horizontally from the center to find the foci. So to the left, 1, 2, 3, 4. That's going to be at negative 6, 1 for one focus. And to the right, 1, 2, 3, 4. That's going to be at 2, 1 for the other focus. The circle for number 4 here is much simpler. All I have to do is find my center. Well, x minus 1, y minus 3, that tells me our center is at 1, 3. And the 16 tells us that r squared equals 16. So r equals 4. The radius is 4. So we go up 1, 2, 3, 4 units. Back 1, 2, 3, 4 units. Down 1, 2, 3, 4 units. And to the right 1, 2, 3, 4 units. And there's our circle. And that's it. Not a whole lot else to describe that circle. And there were other things that we practiced with that, like if we know the focus and the vertices, finding the equations. If there's time at the end of the class today, we'll come back and we'll maybe do another example or two of those. Or even going off of the general equation and doing completing the square in order to graph them. For today, though, we have a pretty large task. It's assumed coming into this course that you have a basic knowledge of trigonometry. But because we need trigonometry for the next section on conics, I want to go back and I want to spend a day or two here reviewing the trig. Now, there are a lot of identities that come out in trig. To make it clear where those identities come from, I want to go over just briefly some of the very basics of trig. Everybody thinks trigonometry is about triangles, and we apply it to triangles. But trigonometry actually comes from a circle. It's parts of a circle. If you have a circle, a tangent is defined as a line or a portion of a line that touches the circle but never enters the circle. So it only contains points that are outside of the circle and one point that's on the circle. A secant contains points that are both inside the circle and outside the circle. We know that a diameter is just a chord. Now a chord contains points, its endpoints are on the circle. A diameter is just a chord that goes through the center of the circle, making it 2 radii. But there's a special diameter that we're concerned with called a reference diameter. The reference diameter is typically the horizontal diameter, but it could be the vertical diameter or whatever. A sine is a value that each point of the circle takes on. The sine for a given point on the circle is the distance from that point to a chosen reference diameter. So for that particular point there, the sine is whatever that distance is, what that length is. So this point over here also has a sine. It would be that length. This point here has a sine. It would be that length. Now in that case, that point being right over the center of the circle, that sine is just going to be equal to the radius of the circle. Well, when we look at trigonometry, we define something called a unit circle. And a unit circle is just a circle where the radius is equal to 1 unit. So we have a circle. There's our reference diameter. Now that reference diameter is going to be 2 units long. Radius is 1 unit long. We define this direction to be the 0 degree direction, and angles wrap around going counterclockwise. So if I can construct an angle here, I want to make it a little more obvious. I'm going to come down here like this. This angle I'm going to call theta. So what I just did there is the Greek symbol theta. Hopefully you've all seen that before. That's just a symbol that's a generic angle or a variable for an angle. Rather than using x or y like we do for lengths, we use Greek letters. We call that theta. Now this length here is the radius of the circle. That's 1 unit. So keep that in mind. That terminal side that we just drew in, the second side, this is referred to as the initial side here. This is the terminal side. That's where the angle ends if we're rotating around the circle. That terminal side defines a point on our circle, right here, that green dot. Well, that point has a sine. That is defined to be, that length is defined to be the sine of that angle theta. Well, we know there's a lot of other trig functions. One of them is a secant. The secant is created by taking that terminal side and extending it outside of the circle. Well, the question is, how far do we extend it? Well, the tangent is tangent to the circle at that reference diameter. So that purple length there is the tangent of that angle theta. In that blue length, which just barely broke outside the circle because of the way my angle is drawn here, that length is the secant of that angle theta. So the secant and the tangent intersect to define each other. Now I should note that this here is also a right angle because a tangent, since it's tangent at the point where that reference diameter hits the circle, a tangent is always perpendicular or a right angle to the radius at the point of tangency. So we've got two circles or two triangles that have been defined there. We've got the small one here, where this is angle theta, this is a right angle, and this is 1 unit here, that's the radius of the circle out to there, and this is the sine of angle theta. But we've got a larger one that's defined. Didn't draw that very well. That's maybe a little bit better. This is still the angle theta, but now this is 1 unit down here. This is 1 unit. This side over here is the tangent of angle theta. And this up here is the secant of that angle theta. Now, most of you probably recognize sine and tangent as being standard trig functions. And those are two of the main trig functions. Technically, secant is the third main trig function, but we tend not to use it. What we use in its place is cosine. That's the button that appears on your calculator rather than secant. Well, where does the cosine come from? Well, the cosine is part of what we call a cofunction. And the cofunctions, co stands for of the complement. So when I ask for the cosine of theta, what that is asking for technically is what is the sine of the complement of theta. Complement, remember, is 90 minus that angle. Well, the complement of theta, if I go back up to my unit circle, complements add up to 90 degrees. Well, if I draw in this vertical diameter here, and I shift my reference diameter to that vertical diameter, this angle here is the complement of theta. That's a right angle here. So those two angles, the brown and the gray, have to add up to 90 degrees. Well, if that's the complement, well then there's that side there. The reference diameter is now that vertical diameter. That length is the sine of that complement. So that length is the cosine of theta. Well, because this forms kind of a little rectangle here, that means that this length down here is the same as that top length. That is the cosine of our angle. So the triangles we've created here define all of our trig functions now. So what that means is up here, this side is the cosine of theta. And that gives us what we call our Pythagorean identities. Oops. No extra charge for the extra chi there. Pythagorean identities. From this first triangle that we drew, this is theta, this is 1, This is sine theta. I'm going to abbreviate it now. This is cosine theta. We know that the legs, the two sides that make up the right angle, and the hypotenuse is the longest side, or the side opposite the right angle. We know that a squared plus b squared equals c squared. Well, here that amounts to the sine of theta squared plus the cosine of theta squared equals 1 squared. Well, 1 squared is just 1. To abbreviate, instead of having to use these parentheses every time we square a trig function, sine squared of theta, we put the squared right after the sine. So that's sine of theta all squared. But we just put the squared right after the sine, so we know the whole function is squared, but we don't have to put those parentheses in. It's strictly a shorthand abbreviation is all it is. So we know that the sine of theta squared plus the cosine of theta squared has to add up to 1. Well, from our other triangle, we have 1 here. This is still theta. This is the secant of theta. This is the tangent of theta. We see the same relationship here, a, b, and c, where a squared now is just 1 squared plus b squared is tangent squared of theta equals c squared, which is secant squared of theta, giving us that Pythagorean identity for relating the tangent to the secant. Now, if I go back up to my unit circle, we said this distance here was the cosine. That would make the cotangent and cosecant off of this reference axis, because we shifted our reference axis. So it would come out something like this. They would intersect out here. So this orange line is the cotangent of theta, and this brown length here is the cosecant of theta. In other words, this is the tangent of the complement. This is the secant of the complement. Well, you can see that forms a large triangle there. Where this is 1. This is the cotangent of theta, and this is the cosecant of theta. And we can see again, we can label them A, B, and C for the two legs and the hypotenuse. A squared is going to be 1 squared plus B squared is cotangent squared of theta equals C squared, which is cosecant squared of theta. So those are our 3 Pythagorean identities. Now you can see they can be arranged. I could subtract 1 here from both sides and get, cotangent squared of theta equals cosecant squared of theta minus 1. But I think at this point we can all recognize variations of a formula like that. Now I'm not going to go over defining each of the functions individually, but we do know that each of those functions represent sides of that triangle. We know that sine of an angle is equal to the length of the opposite side over the hypotenuse. Well, the cosecant of an angle, of that same angle, would be the length of the hypotenuse over the opposite side. So because of that, we see that cosecant, I'll write it over here. The cosecant of an angle is just the reciprocal of the sine of that angle. Similar relationship exists for cosine. Cosine of an angle is the adjacent side length over the length of the hypotenuse. For a secant, that's the length of the hypotenuse over the length of that adjacent side. So here we see that a secant of an angle is just the reciprocal of the cosine of that same angle. The value of the tangent is the length of the opposite side over the length of the adjacent side. The cotangent of that angle is going to be the length of the adjacent side over the length of the opposite side, giving us that the cotangent of an angle is the reciprocal of the tangent of that angle. Now we might also see, since sine is opposite over hypotenuse and cosine is adjacent over hypotenuse, if I take the sine divided by the cosine of that same angle, I have opposite over hypotenuse divided by adjacent over hypotenuse. If I do that division, opposite over hypotenuse multiplied by the reciprocal, so as we instead of divided by adjacent over hypotenuse, it'll be times hypotenuse over adjacent. Well, notice the hypotenuse cancels out. We get opposite over adjacent. Well, that was our definition of tangent. So this gives us one of our ratio identities, where we define that the tangent of an angle is actually could be found by taking the sine of that angle divided by the cosine of that angle. Linked to that, the cotangent, since that's just the reciprocal of the tangent, will be the cosine of that angle over the sine of that angle. So as you can see from these identities so far, if we know a couple of our trig functions, in most cases we can figure out the others just from those trig functions because of the ratios and Pythagorean and reciprocal identities. Well, we also have even and odd identities. Remember what this was is when we talked about even functions and odd functions before? An even function is one where f of negative x is equal to f of x. In other words, it is symmetrical about the y-axis. An odd function is one where f of negative x is equal to negative f of x. It's symmetrical about the origin. Well, in trig, our functions have this relationship. The sine of negative x is equal to the negative of sine x. Sine x is an odd function. It is symmetrical about the origin. The cosine of negative x, however, is equivalent to the cosine of x. Cosine is an even function. It is symmetrical about the y-axis. Tangent of negative x is equal to negative tangent of x. Tangent's also an odd function. It's symmetrical about the origin. So we want to be able to verify trig relationships. We call those relationships identities. When I go to verify identities, the first thing I try to do is I convert every function to sines or cosines. Even the tangents, I put that ratio identity in there to make it sine over cosine. So everything's in terms of sine or cosine. Then I look for one of those other identities. I look for Pythagorean or some other identity to manipulate it to get one side equal to another. When we're verifying an identity, we cannot solve it as an equation. Because when we are verifying an identity, we cannot assume, we can't assume equality. What that means is we can't assume that one side is equal to the other. So that means we can't add or subtract to both sides or multiply or divide both sides. We can only, on each side, we can only replace something with something, another thing that's equivalent to it. But we can't work between the two sides like we do solving an equation. Let's look at an example. So we might have cosecant of x times tangent of x equals secant of x. Now, as I said, the first step I would take here is to change these into sines and cosines. So cosecant of x is 1 over sine x. It's a reciprocal identity. The tangent of x is sine x over cosine x. On the other side, secant of x, well, that's 1 over cosine x. It's the reciprocal of cosine x. So now that I've converted everything into sines and cosines, I look at what I can do. One of the things I can do is I can cancel out common factors, or I can cross-cancel within fractions. Here I have two fractions multiplied together. I can cross-cancel. Sine x and sine x can be divided out, giving me just 1 and 1. So on the left side over here, that leaves me with just 1 over cosine x. Well, on the right side, that's what I already had, was 1 over cosine x. So I have just verified that identity because I have, by replacing things with their equivalents, I have come up with two expressions that are exactly the same on each side of that equation. Let's do a couple other examples. Let's do cosine x times cotangent x equals 1 minus sine squared x over sine of x. So my first step here is going to be to replace everything with sines and cosines. Well, the only thing here that's not a sine or a cosine already is that cotangent. So the cosine x is going to stay the same. Cotangent is cosine x over sine x. So that's all I'm going to change for now. Now looking at this, whenever I see a sine squared or a cosine squared, that should get me thinking about that Pythagorean relationship. Remember, we have sine squared of x plus cosine squared of x equals 1. And there's different variations of that. One variation is I could subtract sine squared of x from both sides. Now I can do that here because this is an identity. We know that that's equal. I can't do anything like that here because we don't know for sure if that's equal or not. So I subtract sine squared x from both sides, giving me that cosine squared x is equal to 1 minus sine squared of x. Well, looking back here, that's what I have right there. 1 minus sine squared of x. That's equivalent to cosine squared of x. So that right side, if I replace 1 minus sine squared of x with cosine squared of x, I have cosine squared of x over sine x. On the left side, if I write this cosine as cosine x over 1, and then I do my algebra, just do my multiplication, Cosine x times cosine x is cosine squared of x. 1 times sine x is sine x. And there we are again. We have the exact same expression on both sides. Cosine squared of x over sine x. Sometimes the manipulation can be a little bit more complex. So let's take cosine squared of x minus sine squared of x equals 2 cosine squared of x minus 1. Well, first thing I see is that the right side of, they're all, by the way, in terms of sine and cosines. That's the first thing I really see. So I don't have to replace anything with sines and cosines. I see that the right side over here is all cosine. So let's try to make the left side all cosines. Well, these are cosine squared and sine squared. So that's going to, again, get me thinking of that Pythagorean identity of sine squared x plus cosine squared x equals 1. I want to replace that sine squared so everything can be in terms of cosine. So I'm going to solve this for cosine squared again, just like I did before. And I get that cosine squared of x is equal, oops, actually let's do it the other way. Let's solve it for sine. So subtract cosine squared of x from both sides this time. And I get that sine squared of x is equal to 1 minus cosine squared of x. Those two, by the way, come up often enough. The one we had up above here, cosine squared of x is equal to 1 minus sine squared of x. And then this one, sine squared of x equals 1 minus cosine squared of x. Those come up often enough that they're worth, putting down in your notes as something that you can refer to. We can't always derive them from that Pythagorean identity, but it's quicker if we don't have to each time. So I'm going to replace this sine squared of x here with 1 minus cosine squared of x. So on this side, I'm not going to do anything. I have 2 cosine squared of x minus 1. On the left side here, I'm going to distribute this negative. I'm going to distribute it as a negative 1. So my cosine squared of x doesn't change. Negative 1 times 1 is negative 1. Negative 1 times negative cosine squared of x is a positive cosine squared of x. Haven't done anything to the right side, so I'm not going to rewrite that at this moment. Here I have cosine squared of x and cosine squared of x, both positive. That's 2 cosine squareds of x, minus the 1 yet. And now I have equivalent, actually exactly the same expression on both sides. Well, sometimes it's not a matter of replacing functions. Sometimes it's a matter of looking at the even or oddness. Let's do, I think this one comes out to be an even or odd deal. Cotangent of negative x times sine of x equals negative cosine of x. Well, cotangent of negative x, cotangent is cosine over sine. So that's cosine of negative x over sine of negative x times sine x equals, I haven't done anything to the negative cosine x on the other side yet. Now I am going to make this sine x into a fraction by putting it over 1 just because we can see here that we're going to end up working with fractions. Then I'm going to use those even and odd identities. Cosine of a negative x is just cosine of x. Sine of negative x, however, is negative sine of x. And I'm multiplying by that sine of x over 1. Well, here I can see I can cross cancel the sine of x. Now I have to be careful. Down here, I have negative sine of x divided by sine x. That leaves me with a negative 1 down there. Here, sine of x divided by sine of x is just a positive 1. So what I have there on the left side, cosine x times 1 is just cosine x. Negative 1 times 1 is a negative 1. Well, cosine x divided by negative 1 is just a negative cosine x. Well, what do we have on the other side? We just had a negative cosine x. So again, we have replaced and substituted on each side till we have equivalent expressions on each side. Let's do one more example together, and then it'll be time for our break. And then I'll put a couple up there for you to work on if you want to, if you come back from break early. So let's do a little bit more difficult one, I believe. Go secant of x minus secant of x over, I didn't need the parentheses there, over cosecant of x plus secant of x equals cotangent x minus 1 over cotangent x plus 1. Now, as always, let's replace each of these functions with sines and cosines. So cosecant of x is 1 over sine of x. Minus secant of x is 1 over cosine of x. This is all over. Cosecant is still 1 over sine x. Plus secant is still 1 over cosine. Cotangent on the right side, well, that is cosine x over sine x minus 1. On bottom, cotangent still cosine x over sine x plus 1. Well, here's what I'm going to do. On the left side over here, I'm going to multiply both the numerator and the denominator of this fraction by cosine x. So here, cosine x times 1 over sine x, that's cosine x over sine x. Cosine x over 1 over cosine x, or negative 1 over cosine x, is just a negative 1. On bottom, cosine x times 1 over sine x is again cosine x over sine x. Cosine x times 1 over cosine x is just a positive 1. We notice that that is now the same as what we have on the right side of that equation. Okay, it is 10:21, so time to take a break. Let's come back at 10:30, and we'll pick up again. I am going to put a couple of them up here for you to work on if you would like, as you're coming back from break. So I'll give you that one and one more here. Okay, go ahead and take your break. Like I said, if you get back early and you want to work on those, please feel free. Otherwise, we'll start going over them at about 11:30. Or 10:30, sorry. Okay, so for our first one here, again, I'm going to go through and replace everything with sines and cosines. So tangent of 5x, that's sine of 5x over cosine of 5x. Cotangent of 5x, that's cosine of 5x over sine of 5x. On bottom, secant of 5x is 1 over cosine of 5x. On the right side, cosecant of 5x is 1 over sine of 5x. Now, I am going to multiply both of these, top and bottom, by cosine of 5x. On bottom, 1 over cosine of 5x times cosine of 5x, that cancels out and gives me just 1. So my denominator is gone. On top up here, well, the first one is going to cancel out as well. The cosine of 5x is on bottom cancels the cosine of 5x I'm multiplying by. So that's just sine of 5x. On the second one, cosine of 5x times cosine of 5x is cosine squared of 5x over sine of 5x. Haven't done anything on the right side yet. That's still 1 over sine of 5x. Now, on this left side, I'm going to leave that sine of 5x by itself. I'm going to get sine of 5x over 1. Cosine of 5x, since my right side's all in terms of sine, I'm going to try to convert my left side all in terms of sine. Cosine squared, remember, it can be thought of as 1 minus sine squared. So that can be 1 minus sine squared of 5x. Still over sine of 5x. The right side, not doing anything with yet. That's still 1 over sine of 5x. We're going to keep that throughout the rest of this. So now here, rather than just cross-canceling and multiplying, I'm adding. And to add, I have to have common denominators. So we're going to use a common denominator of sine of 5x. So that second fraction there is going to stay 1 minus sine squared of 5x over sine of 5x. On the right side, I'm going to multiply the top and bottom by sine of 5x to get a common denominator. So on top, I have sine squared of 5x, and on bottom, I have sine of 5x. Notice now I have a common denominator of sine of 5x. Since I have a common denominator, I can add the numerators. Sine squared of 5x plus 1 minus sine squared of 5x. Well, positive sine squared of 5x and negative sine squared of 5x cancel out, and that just gives me 1 over sine of 5x. And of course, the right side is still just 1 over sine of 5x. Now, there were other ways we could have approached that, but that's the one that I think is probably the most methodical of breaking it down and easiest to follow process. So our second one up here, start out by doing the same thing. We're going to turn it all into sines and cosines. So cosecant of x is 1 over sine x minus 1. Over cotangent is going to be cosine x over sine x. Equals, on the right side, cotangent, cosine x over sine x. Over cosecant is 1 over sine x minus 1. Now I have to, again, we have to work on each side separately. I can't work with both sides at once. On the left side, I'm going to multiply both my numerator and denominator by sine x. In my numerator, 1 over sine x times sine x, that just gives me 1. Negative 1 times sine x, that's just minus sine x. In the denominator, the sine x's cancel out, and I just have cosine x. Well, let's look and see if we can do something on the other side of the equation over here. I'm going to multiply numerator and denominator there also by sine x. Oops, this should have been a plus here, not a minus. There's a plus there. So now on top, sine x cancels out again, giving me just cosine x. On bottom, 1 over sine x times sine x is just 1. Plus 1 times sine x is just sine x. So what we have here I'm going to split each of these fractions up. Actually, I can't totally split that up, can I? So when we look at this, we need to figure out some way to replace some of these in order to make it work. As I'm looking at it, I can see that they're equal, but the process of proving they're equal can't be used right now. I could cross multiply and do that. So what I'm going to do is this right now. I am going to multiply. I'm going to create cosine squared. So to do that, I'm going to multiply the numerator and denominator over here by cosine of x. Just to see what that does for me. So on top, 1 minus sine x times cosine x, that's cosine x minus sine x cosine x. On bottom, it gives me cosine squared of x. Now the reason I'm doing that is because now I can replace cosine squared of x. So I'm going to keep the numerator. Cosine squared of x is going to be replaced with 1 minus sine squared of x. Still trying to figure out if that does us any good. Well, let's see what we can do on the other side. Let's multiply both the top and bottom there by cosine x. So the top, that's going to give us cosine squared of x. On bottom, cosine x plus sine x cosine x. Cosine squared of x, again, I'm going to replace that with 1 minus sine squared of x. On bottom, I'm not going to do anything quite yet. Well, I am going to try to multiply this one then. This one got really cluttered. I'm sorry about that. This was way more difficult than I was trying to give to you. I'm going to multiply this one by 1 plus sine squared x. That's the reciprocal of 1 minus sine squared x. Or not reciprocal, the conjugate, I should say. So I'm going to multiply here by 1 plus sine squared x. Now, I'm feeling like I might be going down a bad path here. But let's back up. I think I've got a way to make this easier on us. Let's back up to this stage right up here. So we're going to rewrite this. I don't like the direction that's going. So let's go back up to that equation. 1 minus sine x over cosine x. Equals cosine x over 1 plus sine x. So what I'm going to do instead is this. I'm going to multiply numerator and denominator here by 1 plus sine x. What that's going to do, on top here, this is the difference of perfect square, or sum and difference product, which is going to give us the difference of perfect squares. 1 squared minus sine squared of x over 1 plus sine x times cosine x is, I'm just going to leave it as 1 times sine, 1 plus minus sine x, or 1 plus sine x times cosine x. I'm going to leave it that way for now. And the reason I'm going to leave it that way is because on top, I can replace 1 minus sine squared x with cosine squared x. And now I can divide out, since cosine squared x is really cosine x times cosine x, I can cancel out one of those, which leaves me with cosine x over 1 plus sine x, which is what I had on the right side. There's a little bit shorter way to get to it than what I was going about there for a minute. How did I know to do that? Well, let me go back and give you a little hint here. What I had here in the blue, one minus sine x over cosine x equals cosine x over 1 plus sine x. I knew those were equal, but I couldn't do the process that shows it, because if I cross multiplied here, if I did 1 minus sine x times 1 plus sine x, I knew that being a sum and difference product was going to give me 1 plus, or 1 minus, I should say, the difference of perfect squares, sine squared x, which is just cosine squared x. Well, then going this way, cosine times cosine is just cosine squared x. But I can't cross multiply in an identity because I can't work with both sides of the equation at once. I have to manipulate each side separately. So I knew that the options were to either multiply this side by the cosine of x, which is what I tried first, and that didn't work, or to multiply this side by the 1 plus sine of x, which is what I did the second time, and that's what worked out for us. So I couldn't actually cross multiply between the two, but I could still multiply the numerator and denominator above one of the sides by what the denominator was on the other side. All right, like I said, that one got a little tougher than I had anticipated. Sorry about that. So there are some other identities that we want to work on, and we want to make sure that we have down. One of them is sum and difference identities. Let's talk about sum identities, or angle sum identities here first. Now, a lot of this is working on the assumption that you guys are familiar with the standard angles. You like sine of 30 degrees is 0.5. Cosine of 60 degrees is 0.5. Sine of 60 degrees is the square root of 3 over 2. Those standard functions. Cosine of 30 degrees is also the square root of 3 over 2. Sine of 45 degrees is the square root of 2 over 2. And cosine of 45 degrees is also the square root of 2 over 2. So it's assuming that you know some of those standard trig values. So the angle sum identities allow us to find the trig function of certain angles if we know some other standard angles to work with. So angle sum identities are talking about adding angles. So if I want to find the cosine of angle A plus angle B, that is equivalent to the cosine of A times the cosine of B minus the sine of A times the sine of B. What does that mean? Well, if I wanted to find the cosine of 15 degrees, well, I don't have that over here, but I can write it as the cosine of 40. Let's see, what do I want to work with there? I guess it really doesn't matter. Let's write it as the cosine of 60 degrees minus 45 degrees. Well, that's the cosine of A. Cosine of 60 degrees is 0.5 times the cosine of B. Cosine of 45 degrees is the square root of 2 over 2. This might be beneficial if I write that 0.5 as 1/2. Minus sine of A. Sine of 60 degrees is the square root of 3 over 2. And sine of 45 degrees is the square root of 2 over 2. Well, 1/2 times the square root of 2 over 2. 1 times the square root of 2 is the square root of 2. 2 times 2 is 4. Minus square root of 3 times the square root of 2 is the square root of 6. 2 times 2 is 4. So that ends up being the square root of 2 minus the square root of 6 over 4. That is the cosine of 15 degrees. So that's a way of expressing it exactly in those terms of those common angles. Well, there are angle sum identities for our other functions as well. So that was the one for cosine. For sine, if I want the sine of angle A plus angle B, that's the sine of angle A times the cosine of angle B plus the cosine of angle A times the sine of angle B. Oops, I did this one out wrong. I did minus there, didn't I? Oops. Cross off that example in your notes. I'll come back and do that. It's the one I should have done with the difference identities. Sorry about that. That's my strike 2 for the day. Now there's an angle sum identity for tangents as well. What I did here, by the way, in case you're wondering, what I found was not the cosine of 15 degrees. What I found was the cosine of 105 degrees. Because this should have been 60 plus 45 is the identity that I used. But for tangent, there is also a sum identity. It's a little bit more complex. Tangent of A plus B is the tangent of A plus the tangent of B over 1 minus the tangent of A times the tangent of B. So those are our angle sum identities. If you can express the angle as the sum of two other angles that we know how to find, we can find their value. So up here, that example, like I said, should have been finding the cosine of 105 degrees. I could express 105 as the sum of 60 plus 45. That's why that identity would have worked for that. There's also angle difference identities. So if I know the difference of two angles, so the cosine, and this is what I should have applied if I was looking for the cosine of 15 degrees, of angle A minus angle B is equivalent to the cosine of A times the sine of B plus the sine of angle A times the cosine of angle B. For sine, the sine of the difference of two angles, so the sine of angle A minus B, is equal to sine of A times the cosine of B minus the cosine of A times the sine of B. And finally, for tangent, the tangent of the difference of two angles, so the tangent of A minus B, is the tangent of A minus the tangent of B over 1 plus tangent of A times the tangent of B. So like I said, these identities really only work if you know those common trig values that I posted up above. But we can also use them for substituting into some of our trig functions. For example, we might find the cosine of 75 degrees. Well, the cosine of 75 degrees, I've got a couple of different ways I can express it. One way I'm going to express it first as the cosine of 45 plus 30. So this is an angle addition. So that means angle sum, I should say. So that means I'm going to use the cosine of A plus B, which is the cosine of A. So this will be the cosine of 45 times the cosine of B, so the cosine of 30, minus the sine of A, so the sine of 45, times the sine of B, so the sine of 30. I know the cosine of 45 is the square root of 2 over 2. The cosine of 30 is the square root of 3 over 2. I'll combine those right now. That's the square root of 6 over 4. Over here, the sine of 45, well, that's still the square root of 2 over 2. Sine of 30 is 0.5 or 1/2. I'll combine those. That's the square root of 2 over 4. Subtracting, that's the square root of 6 minus the square root of 2 over 4. Another way I could have found the cosine of 75 degrees is I could have done the cosine of 120 degrees minus 45 degrees. To do that, I would have to use an angle difference since I'm subtracting. So the cosine difference formula is the cosine of A minus B is the cosine of A, so that's the cosine of 120, times the sine of B, so the sine of 45, plus the sine of A, so the sine of 120, times the cosine of B, so the cosine of 45. Now, the cosine of 120 degrees is just the negative cosine of 60 degrees. So the cosine of 60 degrees is 1/2. The cosine of 120 degrees is a negative 1/2. Sine of 45 is square root of 2 over 2. Let's combine those and get it over with. That's going to be the negative square root of 2 over 4. The next piece, we have the sine of 120. Well, the sine of 120 and the sine of 60 are the same. That's the square root of 3 over 2. Cosine of 45 is the square root of 2 over 2. We'll combine those. Square root of 3 times the square root of 2 is the square root of 6. 2 times 2 is 4. So what we get there is the negative square root of 2 plus square root of 6 over 4, which is equivalent to square root of 6 minus the square root of 2 over 4. Just rearrange that, square root of 6 minus the square root of 2 over 4. So we do get the same result either way of doing it. Okay, so some other angle equivalencies that we need to be aware of. There are half angle equivalencies. So if I'm cutting an angle in half, the sine of theta over 2 is equal to positive or negative square root of 1 minus the cosine of theta all over 2. For cosine of theta over 2, that's equal to plus or minus the square root of 1 plus the cosine of theta over 2. Now notice that both of those turn into cosines. The half angle formula for tangent is a little bit more complex. Mainly because there's different variations of it that are more useful in different circumstances. So the original formula, the main formula for the tangent of theta over 2, or half of theta, is plus or minus. And this makes sense. Remember that tangent is sine over cosine. Is just 1 minus cosine theta over 1 plus cosine theta. But having the square root in there isn't the simplest way to deal with it. So another version of the half angle formula for tangent is that tangent of half of theta, or theta over 2, is 1 minus cosine theta over sine theta. And a third version of that formula is that tangent of theta over 2 is equal to sine theta over 1 plus cosine theta. Now I should explain the plus or minus in front of each of these. That doesn't mean there's two different values. There is only one value, but the formula doesn't give the correct sign. It gives the correct numerical value, the absolute value of that function. You have to decide positive or negative based on what quadrant of the unit circle that angle ends up in. So if theta is 120 degrees, that's 120 degrees. Well, over here, cosine is negative. But half of that 60 degrees over here, cosine is positive. So we're going to use the positive value. Okay, since we have a little time here, I do want to talk about double angle formulas. Now the double angle formulas could be found simply by doing the angle sum formulas using the same angle. The angle sum formula we had, cosine of A plus B, was cosine A times cosine B minus sine A times sine B. Well, if we replace that, a double angle would be basically saying cosine of A plus A. Well, that would be cosine A times cosine A minus sine A times sine A. Well, pretty easy to see that that's just cosine squared minus sine squared. And that actually is our double angle formula for cosine. The cosine of a plus a is expressed as 2a is equal to the cosine squared of a minus the sine squared of a. Now, because of that Pythagorean identity, since there are sines, squareds on the sines and cosines here, there are alternative formulas for that. Cosine of 2a could also be written as 2 cosine squared of a minus 1. Or it could also be written as 1 minus 2 times the sine squared of a. Sine of 2 times an angle of 2a is a little more straightforward. It's simply 2 times the sine of a times the cosine of a. I'll leave it up to you to put that in the angle sum formula and verify it if you want to. The tangent of 2a is 2 times the tangent of a over 1 minus the tangent squared of a. Okay, so those are the double angle formulas. The last one we want to look at is an important one. It's called a power reducing formula, or power reducing identities. These take the form sine squared of theta. Rather than just changing it to 1 minus cosine squared of theta, we can actually reduce the power from a squared down to a linear as 1 minus cosine of 2 theta over 2. Cosine squared of theta can be reduced as 1 plus the cosine of 2 theta over 2. Tangent squared of theta, well, remember it's just sine over cosine, so it's 1 minus cosine of 2 theta over 1 plus cosine of 2 theta. So I've spent about 15 minutes just identifying identities here and throwing formulas out at you. Let's actually apply a couple of them here. So we're going to take a look at an example like let's find here we go. Sine of a plus b times sine of a minus b equals cosine squared of b minus cosine squared of a. So you see here, everything's already in terms of sines and cosines. So there's really nothing to do there. But let's just replace these sums or differences with their definitions. Sine of a plus b is defined to be sine of a times cosine of b plus cosine of a times sine of b. Now I'm putting that in parentheses because up here these two were multiplied. So then the definition for sine a minus b, that's sine of a cosine b minus cosine A sine of B. And of course, we're still looking to see if that is equal to cosine squared of B minus cosine squared of A. This is a sum and difference product. So if I were to FOIL this out, well, let's just do it. Sine A cosine B times sine A cosine B, that's sine squared A cosine squared B. Sine A cosine B times a negative cosine A sine B. Well, that's a negative sine A sine B cosine A cosine B. On the inside, positive cosine A sine B times sine A cosine B. That's a positive sine A sine B cosine A cosine B. Notice those terms are going to cancel out. Then on the last terms, cosine A sine B times negative cosine A sine B, that's a negative cosine squared A and sine squared B. So on the left side here right now, what we have is sine squared A cosine squared B minus cosine squared A sine squared B. So let's see if we can replace those signs and make this work out. Sine squared A is 1 minus cosine squared A. Still times the cosine squared of B. Minus cosine squared of A times sine squared of B. I'm going to write that as 1 minus cosine squared of B. On the left side here, I'll distribute the cosine squared of B. So that's cosine squared of B minus cosine squared of A times cosine squared of B. Over here, I'm going to distribute the negative cosine squared of A. So that's a negative cosine squared of A. Negative times the negative makes this a positive cosine squared of A cosine squared of B. Now you'll notice we have a negative cosine squared A cosine squared B, and this is a positive cosine squared A cosine squared B. Those cancel out, leaving us with just cosine squared B minus cosine squared of A, which was what we had on the other side. These identities are not fun. I admit that. And they're tricky. You're looking at trying to see something and replace it with its equivalent. We're only taking a couple of days on these, which I know means we're not going to get great at them. But the test really, we're not going to overly test you on the identities themselves. What we're going to test you on is how to use them. We need to know about these identities to understand rotation of axes in our conic sections, which is going to be one of the next topics we cover. So for now, I'm going to let you guys off the hook here. I think you guys have heard me say the word sine and cosine enough for one day. We have an old homework assignment from last week, or from last Wednesday, I should say. Old homework from Monday that is due Thursday. Along with that homework, then there is a quiz based on the material from last Wednesday and Monday that is due Friday. And then there's a new homework on the material we covered today that will be due next Tuesday. And yes, next week, Monday, class will be in session as normal. Wednesday, of course, the campuses are closed. So there are no classes. This class will not meet next Wednesday. So anybody have any questions? Okay. Realize this is a frustrating topic, so be patient with yourself. It's going to take a little practice, and Like I said, it's not something I'm expecting you to be an expert at when we're done here. So give it your best shot. You guys have a great day, and we will see you on Monday.